Hello all, welcome to the next and final video lecture of the module 1 in control systems. So that is signal flow graphs concepts and also the Mason-Gain formula, which is very most important to solve the signal flow graphs. It is a extension or a continuation of the block diagram reduction. Block diagram reduction is related to the blocks, but it is related to the signals where it is will be represented in a different format. Okay. And in this video lecture, we are going to cover about what are all the signal flow graphs and how it can be able to reduce and how it can be able to take into considerations. Okay, and where it can be used and everything. Okay. And what is a signal flow graph is simply if you see this diagram itself, you can understand like that this is the signal flow graphs can be represented. A signal flow graph is something like it is a representation in a graphical way and which is able to see the linear algebraic equation. Like for example, here B, G, C, D, I, H, J, these are all related to the one some of the signal. That means either it can be feedback signal, either it can be input signal, either it can be output signal, or whatever it will be. And these are all wherever to this point of intersections are there, they are considered as the nodes, and wherever it is they considered as whatever the signal will be there, they are considered as the branches, loops, and everything. So based upon if you know the circuits, how it will be. Reductions are happening in the network reductions, in the same way it is happening in this way also. The same way signal flow graphs also it can be reduced. Okay, and why we need to use the signal flow graphs, because signal flow graphs are very powerful because it can be easily can able to understand the system equations, and also when you are having a multiple inputs and also multiple outputs and multiple internal equations also there, if there we can able to use our this signal flow graphs so to reduce this each and everything to understand every point of contact, every point of intersections, every point of considerations also. And also the thing is most oftenly it is a connectivity to the block diagrams, whether it can be in a complex interaction. When you are going into the block diagrams, it may have a somewhat little bit of complexity, because one battery can be represented in one diagram, but here we are not representing any batteries or anything. We can able to take the considerations of the elements also. And the next is components of a signal flow graph. There are many components other, like for example there are nodes will be there wherever the points are connecting, that is considered as a nodes, which is represented as a system variable. That means either it can be some point of like a voltage, current, or something itself like that. And also like the director branch, that means which is related to the gain. That means either it can be addition, or it can be a consuming, or either it can be a editing element also, that can be done. And also input and output, which can able to see the Laplace domains, like as we already know, when we are writing a Laplace domain equations, we need to take the considerations of the inputs and outputs. So there the input nodes and output nodes can be considered there itself. And the next one is, for example, let's take it as a in this total lecture I am not going to draw any signal flow graphs for representation of all examples, because I'm going to consider or I'm going to say especially this video in perspective of the gate terminology, because in the gate nowadays they are not going to give the diagrammatic representation, they are giving that whole description in the wordings. So that's why I'm just driving you to take the in the same format. Okay, so if you see this is the one of the signal flow graph diagram. So if you see x2 equal to ax1, x3 equal to bx2, and x4 equal to cx3. If you see a, b, c, these are all maybe the gains, or maybe it can be represented in uh, the feedback loops also. So they will give, like for example, if you see, we can draw the nodes x1 to x4 and connecting them with ABC gains. That means that whatever the gain through that one, they can be considered as the ABC. That means they are all representing in the single line diagram itself. Or some diagrams like a x2 can be represented to the, that means they are interconnected, or it can be like a feedback signals or something will be there. So these things you can simply you can draw and you can understand by simply representing the connecting line itself. You can easily understand this signal flow graph diagram. And when it comes to the forward pass and loops, you need to very careful understand that this forward pass or loops cannot be repeated. But when you are writing the signal flow graph diagrams or signal flow graph equations, once you considered one forward loop or forward thing, so you don't need to consider again the same node or same thing multiple times. That makes a thing things call it as it will be represented in a multiple bigger loops. So to represent that one, we need to apply the Mason-Gain formula to reduce all these things. So what is Mason-Gain formula means? Mason-Gain formula is to use it to find the transfer function, where we can able to, here if you see t, that means total transfer function is equals to the summation of the total gains pk is related to p of k is related to the gains in every path, and also delta k is related to the which is related to the total summation of the remaining apart from the gains, whatever the summation will be there, that will be related to that one, and up to k path. If you see delta, which is related, is 1 minus sum of individual loop paths plus sum of gain products of non-touching loop also. That means here some loop paths will be there which can be able to the touching, and some paths will be not able to touch also. So they also need to be considered when you are writing one of the transfer function, because they may be indirectly representing on the element, sometimes they may be directly represented. So all need to be considered. So this is how we need to represent one signal flow graphs representation to the Mason-Gain formula. So here we see the step-by-step representation of the Mason-Gain formula. Let's take it as, for example, let's apply this to a simple SFG, that means signal flow graph. So I'm considering x1, x2, x3. This is the thing, and a loop, call it as a x2 having a gain of minus g, and also forward path gain of g1 and g2. Okay, and loop gain is whatever the loop gain we already discussed, that is minus h. Then automatically what will happen? So loop gain is 1 minus total. First we need to find out the delta, that is 1 minus of loop gains plus non-touching loops will be there. Here they are not giving any non-touching loops, nothing is there. Only the touching loops are there. That is the only the x2 that is having a loop gain of minus h. So that whatever the delta is, that is will come like the 1 plus h, and also whatever the delta 1. Here no nothing is, no non-touching loops are there. So that's why we need to consider that delta 1 as a 1 itself. So totally the total transfer function will be represented as g1 into g2, that means forward path gain of g1 and g2 into 1 of non-touching loops by total of 1 plus h. So this is how it will be considered. Okay, and the next one is related to the handling multiple loops. For example, if you are having multiple loops or multiple paths will be there, then how you need to consider, because when you are doing multiple loops you can get confused wherever you are taking, wherever you are getting. So regarding that thing, we need to take these considerations. So if the multiple forward paths and non-touching loops are ready, then first we need to find out the gains first, and after that the whatever the other, apart from the gains, whatever the summation amount is that we need to find out. And after that, what are all the loop combinations? First we need to understand the don't touch, and after that we need to find out the touching loops. So then we can able to reduce all the things into structural format and also step by step way. So this is how we can able to reduce very high signal flow graph also into a very step by step manner. Then you can easily understand. Otherwise, if you're doing in between internal loops or something like that, then automatically you get able to get confused. And the next is complex example. If you like say, let's take it as a, this is another complex example. I'm taking it as a 2 forward paths and also 3 loops and 1 pair of non-touching loops. Here we can calculate the P1, P2. That means the total forward paths P1, P2 and the loops, and also will be there, and the delta, total delta, and the 2 non-touching loops. That way delta 1 and delta 2 are related to the 2 non-touching loops. Then you can apply total everything into the Mason-Gain formula. Then you can able to get the things. Okay, and here you're going to see about the where you can able to use this practical applications. So because that is important. So practical applications where we are using is we can able to use in the control system modeling, and mostly as I already said in the first in the initial of this video itself, we are using in the network reduction. In the same way here the circuit analysis also we can able to use, and also digital filters and communication systems where we can able to make more reliable, more things into consider. Okay, and the next thing is common mistakes. As we already, when we are already discussed the block diagram reduction technique, common mistakes can able to done. In the same way, the signal flow graphs also some common mistakes can able to done. So regarding that one itself, so you need to see the touching loops, non-touching loops, incorrect loops, ignoring feedback loops. So these are all need to be very carefully. You need to check one by one. Once you are looking into the loop combinations and non-touching loop, especially the non-touching loop conditions. Okay, so then only you can get able to reduce the signal flow graphs in a simple manner. Otherwise, it will be get very worse and very wide. Okay, so up to this, the module 1 is completed. Thank you.